Hello. In this lesson, we're going to talk about what is a wave and what do waves have to do with light. Let's first of all start by defining what a wave is. The wave, or a wave, is a transfer of energy without the transfer of matter. And the way this works is we cause a disturbance in some medium, and we're able to transfer the energy from that disturbance to another location without actually having to move the matter itself. The parts of a wave include the crest, which is the top part of the wave, and the trough, which is the bottom part of the wave. You also have the amplitude, which is the distance from the middle point on the wave, and the wavelength, which is measured from crest to crest or trough to trough. The wave itself we've seen in the lab that preceded this video. Now, we can actually do some calculations with this wave, which is what we've done in the video, by looking at some of the previous equations we have, such as the velocity of the wave. We can measure, or we can calculate how fast the energy is transferring through the medium by looking at this equation. It tells me that the velocity of the wave equals the displacement of the wave, or displacement divided by time. So velocity equals delta x divided by delta t. Now what this means is if I look here, if I look at the amount of time it takes for one wavelength, that's my delta x. So if I look at the amount of time it takes one wavelength to go from here and for this next wave to travel through, that is exactly equal to the time period. So I know that the velocity of the wave, or the speed of the wave, is the wavelength divided by the time period. Now using another equation, which we've learned in the last lesson, the frequency equals 1 over the time period. Well, if I look here, this can be written as the wavelength times 1 over the time period. And so by using this equation down here, I get that the velocity of a wave equals the wavelength times the frequency. Okay, so this is one of the basic equations of waves. Now we're going to apply this to light later on, but right now let's look at some of the properties of light. So here's the properties of light. Now, one thing about light is it comes in little packets called photons. Now these packets have both wave and particle properties. Now Einstein came up with his special theory of relativity. And it came up with the idea that all light travels at a constant speed in a vacuum. Now light can actually change its speed as it goes from one medium to another, and we'll see that later. But the speed of light is going to be equal to this variable c. So the speed of light is c. All right, and it's 300 million meters in 1 second, or 3.00 times 10 to the 8 meters per second. Now, when we start talking about light, we also look at what's called the electromagnetic spectrum. Now, light consists of just a very small portion of this spectrum, as in this area right here. It is just a small portion of the electromagnetic frequencies that are out there. We start off with the lowest wavelength, the biggest wavelength and the lowest frequency, and those are radio waves. This is what you get on your radio when you're driving on the road listening to the radio. And then you get microwaves, which a lot of cell phones run off of microwaves. It's also what your microwave at home uses to cook your food. You then have infrared waves, which are heat waves. You have the visible spectrum. And then you have the ultraviolet rays. These are the ones that are harmful, that cause skin cancer and sunburns. You have X-rays, which can cause cancer and can cause or allow us to actually look through the body at more dense substances such as your bones. And then you have gamma rays. Now, gamma rays are very harmful. They do not turn you into the Incredible Hulk, but they are harmful and they do cause serious damage to your tissue. Now, visible light is the one that we're really worried about because that's the one that we can pick up on as human beings. Now, the visible light spectrum actually has a wavelength of 700 nanometers, and that equals red light, which is the largest wavelength that we have. And then for purple light, violet light, you have 400 nanometers, which equals violet. Now the spectrum for light actually follows Roy G. Biv. R-O-Y-G-B-I-V. Now the R in Roy G. Biv stands for red. And then you have O, which is orange. You have yellow. You have green, blue, indigo, and violet. Now the energy associated with these colors increase as you go to the right. So radio waves has the lowest energy, and gamma rays have the highest energy. Same thing with the colors. Red has the lowest energy, so that's the lowest. And violet has the largest energy, or the greatest energy, so that's the highest. Now let's talk about what is light. So we know the properties of light. Well, let's talk about what it is. Now, light is a combination of both an electric and magnetic fields. Electric fields are caused by charged particles that are close to each other. And this is how your radio works to push out or to get radio waves. It causes electrons, which are electrically charged, to vibrate. And that produces an electric field, and it also produces a magnetic field. And here we have a picture of, or an animated picture of an electromagnetic wave. The yellow or the orange here is the electric fields, and the magnetic fields are the purple. Now, one thing you can notice about this is that those fields are 90 degrees to each other. They're always perpendicular. Now, the way that light is created is it's created by an excited electron that's in a higher energy state than it normally is, and whenever it falls back to its lowest energy state, it emits one of those photons. So here we have a charged particle that gets shot into, this looks like a hydrogen atom because it just has one proton and one electron, and it elevates that electron to a higher energy state. Now, whenever that electron falls back down, the electron, because it loses energy, actually emits a photon. And this is how light is created in LEDs. This is how light is created in incandescent light bulbs. This is how radio waves, or the electromagnetic waves, are produced. Now, the farther this falls, the higher the frequency, the greater the energy of the photon that's emitted. And if it doesn't fall that far, then you get lower frequency wavelengths. Now, what proof do we have that light is like a wave? Well, the biggest proof that we can use right now is called interference. And this is caused by two waves that crash into each other. We see this in light just the same. We see this in light only whenever the light is of the same phase and the same frequency. This is called monochromatic and coherent light. Now, lasers produce this kind of light. So we've talked about lasers. We'll have lasers in class, but lasers actually produce this kind of light. Now, if I look at interference on just regular waves, here I have two waves, and these are called in-phase waves. If I notice, they follow each other. Now, whenever I have a crest that meets a crest, I get constructive interference, which means that these two crests add to each other. And so I get a wave that's much bigger, or that's exactly equal to 2 times the amplitude. I also, whenever I get a trough meets a trough, I get constructive interference, and I get a trough that is equal to 2 times the amplitude. So I get a larger wave. Now, if the waves are not in phase, or what's called antiphase, in other words, I have a crest that meets a trough and a trough that meets a crest, well, it's called destructive interference, which means that this trough cancels out that crest, and I get a flat line for my interference wave. So the sum of two waves that are in phase gets me a larger amplitude, a higher energy wave, and a result of two waves that are not in phase, I get cancellation, or a no energy or a lower energy wave. Now, we can actually see this in a simulation on PhET, and here I have a water droplet. Okay, and I'm going to go ahead and pull this over and make it bigger so that we can see it. And so here I have a water in a faucet. Now, this is probably the one thing that we know of that actually produces waves that we can see without any kind of special equipment. Now, in order to see interference, I need to have two waves going at the same time. And I'm going to increase the frequency so we can see this interference more. Now, as this goes on, you're actually going to see places where we have large or very dark troughs and very light crests. And we also have places here that are kind of muddled and kind of unfocused. And these are the places where we see total destructive interference, and these are the places where we see total constructive interference. If I add a detector, I can actually look at these spots. So let's look at one that is totally constructive interference. All right. If I look at totally constructive interference, which is right here on these deep ones, I notice that my wave looks like this over here. Now, if I move it to one of the faded ones, you notice how my wave almost cancels out. And I could probably find a spot where it cancels out completely if I had time. There we go, right about there. The wave itself actually cancels out, and this is called destructive interference. Now, if I look at light, here's a laser, and it's emitting a pulse of, or pulses of red light. Now, in order to get that interference pattern, I have to use two lights. And we can actually see now that it's starting to look like the water waves. If I add my detector, I can once again look at these total constructive interference, and I notice that my wave is very tall. I get a lot of energy, a lot of amplitude. If I look at the parts that are kind of faded, my amplitude goes almost to nothing. It's almost a flat line because the light there cancels out. Now, you can actually see what this looks like if I were to project this onto the wall or onto a screen. I get spots where I have bright intensity light, which is where I have constructive interference, and I get places where I have almost no light or no light at all. And this is total destructive interference. Now, this is one of the greatest evidences that we have to show that light behaves as waves. That concludes the light and wave comparison.